Hello and welcome to section 4.3 Riemann Sums and the definite integral. Alright, so there's a lot of writing on this page and you don't really need to get all of this down, but I wanted to kind of show it to you, and you should probably read through it to make sure that you kind of understand what's going on here. But what Reimann basically did is he realized that all the things we were doing before dealt with the same size rectangles. If we had all the rectangles the same size, then you could find the area under the curve quite nicely. He said, well, you know, as a devil's advocate, he said, do they have to be the same size? And so what he basically did is he said, no, they don't. They don't have to be the same size. So we can make the delta x not have all of them be exactly the same size, but we could kind of norm them, and even if they weren't the same size, we could kind of average them and find out what's going on. So our delta x is not going to change. So Reimann is making a connection between the summation formulas and the integrals that we were going to talk about in the near future. So he's the guy that made the connection. So if they ever ask you to use a Reimann sum, then you're going to be basically doing the same type of summation that we've been doing before in the previous section in 4.2. But it's just a matter of that, you know, you don't have to have the same size rectangles. So you could if they gave you something with a drawing, you don't have to use all of them exactly the same size to find the area. You could use the ones that fit best. So what he decided is that in this that the definite integral can actually help us find area. And so we're basically we're giving you a function, say something like f of x here. This would be f of x. Then if we go between if we pick a and we pick b, and we can find the area by using the definite integral, which is the symbol that he kind of came up with or used to represent the summation. And so this thing is equal to the summation, and he's using an infinite amount of rectangles of varying sizes that will basically find the area fairly accurately under this curve. So here are some geometric examples of what's happening. And so if I was to do the summation of this, now remember that this is just saying we're going to make our limit as n goes to infinity, the summation from 1 to n of 4. Well, that would mean that if I made my number of rectangles go to infinity, then this would just be 4 times n. Well, that doesn't quite work for this, because that would mean that I'd have an infinite number, and so I would end up having to use my value, that the width of my rectangle in this case is just 2, so n would be 2, and so I end up with an area of like 8. Alright, and so all of these are just connecting the area of a geometric shape to what we're used to. And so you'll notice that the height of this trapezoid, the base is 2, this base over here is 5, and the height of the trapezoid is the distance between. So this definite integral between 0 and 3 would be found by taking 1/2 of the two bases added together and multiplying that by 3. And so we would end up with, it looks like 21/2 would be my area under that curve. And so it's just a matter of this is just a connection between area and geometric shapes that we have dealt with, and so on and so forth. So if you're looking at this shape, we have a radius of 2. You can see that it's a half a circle, so we're going to use 1/2 pi r squared. And so when we actually are able to find the area under this curve using definite integrals, then you'll be able to come back and check these. But this would be 1/2 pi times 2 squared, which would then give me something like 2 pi for my area. And so this summation stuff that we're talking about up here, well, we'll come back to that again, but we're just going to say that there's going to be a connection, and you guys will see that as we go along. Well, we could say a couple other things that we have here is that we have a definite integral. If we go from the same value from a to a, we're going to get 0, because there's no width to the rectangle. If we go from b to a, it's the same as going from a to b, but switching the sign. So a couple quick little examples down here, that if I go from pi to pi of sine, then that's going to be 0. And I could rewrite this one, which would be a better way to write this, always trying to keep the lower one on the bottom, the smaller number on the bottom, would look like this. And so then from there, if we wanted to, we could go ahead and solve that problem. And we would end up saying, oh, well, that's basically the same problem we just had for the trapezoid, and that would be 21 halves. Now, I know this is starting to seem a little bit, a negative 21 halves. This is starting to seem a little bit like a mystery because I'm not giving you all the information. But when we do these problems, we will be using summations. And we won't be given a curve that will be, or we won't be given a shape that we can easily tell. And again, we're going to practice this in class. And so then here's the last thing that we have here. Basically what they're saying in this is that if we have two functions, f of x and g of x, and we have something like f of x is smaller than g of x, then if we're picking between two points, a to b, then the area of f of x will remain smaller, because it's a lower function than the area of g of x. And that's really all this is saying. And we don't use this very often, but it is something that just to kind of pay attention to. So these are our notes for section 4.3 Riemann sum. And I promise you that when we come to class, we can clear up a lot of these things. But please bring your questions, and we will talk more about this in class.